Hello, in this video we will be discussing the kinetics of a human leg lifting a weight on a leg extension machine. Kinetics is the study of the relation between the forces acting on a body, the mass of the body, and the motion of the body. We use kinetics to predict the motion caused by given forces or to determine the forces required to produce a given motion. One way to solve these forces is by utilizing Newton's second law, force equals mass times acceleration. The law states that the resultant force acting on a particle is not zero. The particle has an acceleration proportional to the magnitude of the resultant and in the direction of this resultant force. Our topic focuses specifically on the kinetics of a rigid body and rotational motion. To execute a problem with rotational motion, you'll need to know the following.
Angular velocity, omega, and angular acceleration, alpha, are both just subsets of traditional linear velocity. Linear motion can be easily converted into components with the following equations. One, where velocity is going to be equal to omega cross r, and the second, where linear acceleration is going to be equal to alpha cross r plus omega cross r. As you can see, velocity is simply the rotational force across the distance, which works out unitwise. However, acceleration ends up looking more complicated than before. This is due to the two components of rotational acceleration that arise when you convert linear acceleration. The two of these are normal acceleration and tangential acceleration. When you have an object rolling at some non-constant speed, you can expect a normal acceleration to appear that would act inward, and a tangential acceleration acting down or up, depending on the direction of rotation. The relative motion equations are also extremely important for rigid bodies. As a rule of thumb, pick a point that's not moving. If that's not feasible, pick a point whose motion is restricted to only one direction. For example, a piston locked into a slot. Taking a look at some of the relative motion equations, in the equation v sub o is equal to v sub a plus v sub o slash a, you would want to select some point a whose motion was either zero or constrained. When you move into kinetics, dimensions such as width are added, and you return to the basic format for F equals ma problems, where you have the sum of the forces on the free body diagram equal to sum of the forces on the mass acceleration diagram. The problem that arises is that now you're going to have the sum of moment equations as well as the sum of forces equations. When we had particles, we didn't have dimensions, so sum of moments did not need to be considered. Whereas mass is a reluctance to accelerate, I bar is going to be equal to the mass moment of inertia, which acts as a reluctance to rotate. Acceleration then simply turns into angular acceleration, alpha. I bar alpha is always going to be drawn about the object's center of mass, typically labeled g, and linear accelerations are drawn as normal, also going through the object's center of mass.
By applying everything we just learned, we can solve for the reaction forces in the knee joint during the leg extension exercise. Because of the complexity of the leg shape, we are going to assume the body to resemble a slender rod. In this example, we are going to assume that the leg lifts at a constant angular velocity and the force the muscle exerts is known. First, we're going to draw the free body diagram. We will place the weight of the leg at its center of mass. In reality, the center of mass of the lower leg is not right in the middle, but we're going to approximate the lower leg to be a slender rod and place all of the weight at the centroid of this shape, G. The weight applied to the leg by the machine will be located at the ankle and will be directed straight down. Next, we will add the reactions at the knee. We will assume the knee is a pin joint because it can freely rotate but cannot move in the X or Y directions. Therefore, we have two reactions at the knee joint, one in the X and one in the Y direction. Finally, we can see that there is some force provided from the quadricep muscle making the lower leg lift the applied load. We know this because the muscle contracts during the exercise. So, we will place that force at some angle, some distance from the knee joint. This force is difficult to measure, but for the sake of this problem, we will assume it and its angle are known. Next, we will draw the mass acceleration diagram. We will treat all forces as if they act on the center of mass. The leg rotates about fixed point O, and the acceleration of the center of mass can be broken into components. Finally, we add in the rotational equivalent of mass times acceleration, I bar alpha, about the center of mass. However, our leg is assumed to be rotating at a constant angular velocity, so this becomes zero. Now we are going to solve for the reactions at the knee joint. To do this, we will equate the free body diagram and mass acceleration diagram forces, starting in the X direction. In the Y direction, and taking moments about the point O. At this point, we have 3 equations but 4 unknowns, so we will need another equation. We can find this 4th equation in relative accelerations. For this example, we will relate the center of mass, g, to the fixed point O. We first need to understand the motion of each point. Point G has 2 components of acceleration. O is fixed, and point G relative to point O rotates in a circle about O. We can split the acceleration of G relative to O into normal and tangential components, and the tangential component will go to 0 because there is no angular acceleration. Summing the x and y components gives us the following. Now that we have solved for all of the unknowns, we can plug these expressions back into equation 1, equation 2, and solve for the resultant reaction at point O.